So let's start off by looking at the largest floating point number, and we'll see what happens whenever we allow the number to overflow to plus infinity whenever we use the multiplication tool. So let's create the largest number. So this is the largest number here. So we're going to copy this and we'll paste it into the multiplication tool. So we'll paste the largest normal number in, and this is this number here, and you can see it in the hex is 7f, 7 and 5f's, and again this is the same number we've seen just a second ago. Now obviously if we multiply this by a value of 1, we should get the same number. So we multiply it by 1 and we get the same number, 7f, 7 all f's. Now if we were to multiply this by a number which is slightly larger than 1, then it should tend off towards plus infinity. So for example, if I multiplied it by 1.1, then you can see that it's tended off to plus infinity. So in fact that's a multiplication that produces an overflow to plus infinity. Now the interesting thing that you can do here is you can check and see how many significant figures we can actually work with here. So for example, if I was to multiply this by 1.01, then again we're still going to get plus infinity, and we keep adding the zeros until eventually what's going to happen is that this number here is going to round to a value of 1. So the number of significant digits, so it should be the next one now, I think it's this one here, and you can see that this number here, 1.000000, so that's 1, 2, 3, 4, 5, 6, 7 zeros and a 1. This sits in the actual 1 bin because we've only got a single precision floating point number system here, so it's only accurate to a certain number of significant figures. So in this case it's accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's accurate here to 9 significant figures. So for example, if I was to put another 0 in here, it would remain exactly the same because this number here will fall into the same bin as this number. So let's look and see what happens when we put a number, say 0.9 in. So we're going to get a number which again is a normalised number, and if we were to put 0.99, we can see here it's a normal times a normal giving a normal result. And we can continue putting these 0.9s in, but eventually what will happen is this number 0.999 will tend towards a value of 1. So again, when we get to about 9 significant figures, it'll change to a value of 1. So this is the actual value for 1. So that's going to be our 1, 2, 3, 4, 5, 6, 7, 8 decimal places here. So now let's look at the smallest normal number, and that's the smallest normal number there. Now again, we're going to do the multiplication on this in order to see what happens at the junction between the largest subnormal and the smallest normal number. So let's copy this one here and we'll paste it into the multiplication tool. So now we can put in the smallest normal number, which we've just seen a second ago. So this is the smallest normal number here. If we multiply it by a value of 1, then we're going to get the same value. Okay, so there's no surprise there. Now if we were to multiply that by a value any less than 1, then this is going to tend towards a subnormal number. So when it will tend towards the largest subnormal number. So let's say we multiply it by 0.9, and you can see that we've got the subnormal number. Now if we were to multiply it by 0.99, then what's going to happen is we're going to tend towards the largest subnormal number. But eventually what's going to happen is that the 0.999 here will head into the bucket which says 1, and at that point we're just going to be left with our normal number again. And you can see this happening here. At this point here we've got all 1s here, so if you head into the next one there, you can see it's now jumped from the largest subnormal number to the smallest normal number. And we can see again that it's going to be accurate to a certain number of decimal places, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8 decimal places. Again, if we were to take this away, then we would head back into towards the largest subnormal number. So let's see what happens when we overflow or underflow to 0. So now let's look at the smallest subnormal number. So that's the smallest subnormal number, and again what we'll do is we'll copy this number here and we'll paste it into the multiplication tool. So we'll put the smallest subnormal number in, so that's this number here, e to the minus 45. Again we can multiply it by a value of 1 and we'll get nothing other than just the smallest subnormal number. Now obviously if we multiply this by anything less than 1, then we're going to go beyond the smallest subnormal number, and this will be an underflow to 0. So if I multiply that by 0.9, then as we expect we underflow to 0. But again we could multiply it by 0.99 and then 999, and we can continue doing this until eventually what's going to happen is that this 0.999 is going to fall into the bucket which says 1. Okay, so this one here will soon change. If you check the numbers out here, we can see it's all ones here apart from that one, so we've got another one to go. Now whenever we went through that junction there from 1, 2, 3, 4, 5, 6, 7 nines to 8 nines, this number here has now jumped up to a value of 1, and again we've now got the smallest subnormal number. So it now shows you the number of significant figures that we can use for our single precision floating point multiplication. So that's all there is for this video. It's just a quick introduction just to show you the junction between each of the number types and what happens when we're multiplying, and it shows you the number of significant figures that we can expect from a single precision floating point multiplication. Now just to be clear as well, that whenever I've coded this in, and this is done in Excel VBA, I haven't cheated. I haven't decided to multiply the two numbers together in the VBA code and then check and see and compare it to the correct answers. I have actually ran through a process which models what would happen if the input was purely a digital or a binary input. So again, I'll go through that in another video, and if you like, and I can get some more explanation to the code in the background here. So thank you for listening. I'll get you in the next video. Goodbye.